depending on which amino acid you change and how you change it. Some mutations may be dominant, some mutations may be recessive. And so you're getting an insight now into the molecular nature of how a change at the DNA level changes the phenotype. Totally different phenotypes from two different single nucleotide mutations. Any questions on that? So, oncogenes are the second category of genes that cause mutation, that cause cancer. The third category, the third group of genes, are tumor suppressor genes. So this is all great, but remember, you have this checkpoint here. It's a really good checkpoint. That checkpoint will save your life. You cannot get cancer with a RAS oncogene mutation. I know we just went through it. That whole process will be just as I've outlined on the board, but that cell with a single oncogene mutation will not develop cancer as long as all of your tumor suppressor genes are okay. The tumor suppressor genes are the genes that are managing this checkpoint. Now, the oncogenes are really nice because the overwhelming vast majority of them fit into just 5 categories. Can't do that with the tumor suppressor gene. There are all sorts of things, and everything we talked about on Monday, all the things with contact inhibition, all that stuff. There are dozens, if not hundreds, of different genes that fall under the category of tumor suppressor. That is, they suppress cancer. As long as they're intact, that RAS is not going to cause cancer. Potential, but it won't happen unless we knock out the tumor suppressor genes. So to get cancer, you've got to have a whole list of mutants. That's what I said when we started this. Cancer is not a single gene mutation. Cancer is a collection, a multi-genic disease. And so the major checkpoint is a gene called RB, which stands for retinoblastoma. Again, retinoblastoma is a gene like RAS. It is probably mutant in half to 3/4 of all cancers. It's that important. It is the guardian. It stands at the border of S phase and said, I don't care that you're mutant RAS, you are not getting in. Go away. Literally, it is your guardian against a single mutant RAS oncogene. So retinoblastoma is a cancer of the retina in your eye, which is really unusual, and there is no explanation. This is a gene that is active and working in this, doing exactly what I have here in every single living cell in your body. Now, I've written it with a capital R, but the reality is that it's not a dominant gene. Remember, that was supposed to be the terminology. In animal cells, if we write the gene name with a capital letter, it says that the mutation is dominant. But people were fooled for a long time. Here's the story. All of a sudden, a child gets retinal cancer at the age of 5, 4, 5, and he loses one eye. And then a year or two later, the other eye goes and he loses that, he or she. Even though the gene works in every single cell for reasons that nobody understands, the eye, the retina, is the one that has that happen. And so for you women, you know BRAC1. Everybody knows BRAC1. It's a universal gene. It's not a gene that's only expressed in breast tissue. It's a universal gene, and yet, when it's mutant, it causes primarily breast cancer. There is no explanation. The genes that we're talking about are universal, working in every single cell, and yet there's a whole long list of genes that even though they function identically in every single cell, they cause a very specific, primarily, type of cancer. And so retinoblastoma is one of those genes. It is the guardian of the cell cycle. You cannot get into the cell cycle with an intact retinoblastoma. So we're going to talk a little bit about retinoblastoma and a gene called P53. So we have 5 oncogenes that we talked about. We're just going to talk about 2 tumor suppressor genes. So retinoblastoma is the checkpoint protein. P53 is the damage sensor. P stands for protein. 53 stands for the molecular weight. It is 53,000, it's a protein of 53,000 molecular weight units. Because it was first picked up as a protein with unusual properties in cancer cells, and just labeled P53, protein of this size, and then somebody figured out how important it was, but that name stuck. Yes?
So wait a minute, you said that retinoblastoma is supposed to be the actual gene, the actual protein bleeded?
Retinoblastoma is the checkpoint gene. That is the ultimate in a relay system that I'm going to describe to you. The ultimate that has to give approval for entry into S phase. As long as RB's there, you're not going to go into S phase unless those conditions that you learned for the first exam, adequate growth and no DNA damage. So remember, in order to get cancer, you've got to have mutator genes. You've got to have lost the ability to repair all your genes properly. Now, P53 is all about DNA damage. It is not a sensor. It is simply a relay. We talked about DNA damage repair. So there are sensors. You have genes that code for sensors. You have a gene that codes for a protein that recognizes thymine dimers. You have genes that code for all kinds of proteins that recognize all sorts of mutant DNA bases. Anything not A, G, C, or T. As soon as that sensor recognizes, let's take thymine dimers. As soon as it recognizes thymine dimers, it binds to it as a beacon. The repair system comes in, has to alter the chromatin, and at the same time, it sends out a signal to P53 in the nucleus, hey, we've got damage. P53 then inhibits retinoblastoma. So that's the relay. P53 is getting information from the nucleus that there's damage. So the nuclear sensors, it's a kinase relay, a relay of 3 or 4 protein kinases, where the major one phosphorylates, the secondary which phosphorylates, the tertiary, which goes out in the nucleus and signals P53. Doesn't phosphorylate, I don't want to read that. So as long as there is damage, P53 through another set of proteins, again, really complex. I'm just getting to the outline. P53 halts RB and doesn't let RB release the cell. Everybody see what's happening? So there are two possible outcomes. P53 is actually a gene regulator. So when this happens, one of the things that's going to occur is P53 is going to go into the nucleus itself and turn on DNA repair genes. And so P53 is going to start the process to speed up repair. But let's say you've been out and you really got sunburned. You got a lot of thymine dimers. If the amount, so each thymine dimer is going to have a beacon, going to have a relay sending information out. If the damage is too much, so P53 itself will either cause the cell to halt the cell cycle, so if the damage is light, not a lot of damage, we're just going to halt the cell cycle and let the repair system work, and so G1 just gets longer. No big deal. As soon as all those sensors go away, phosphatases and alpha kinases remove all those phosphate groups, and P53 then lifts its embargo on RB. RB says go ahead and replicate. But if the damage is too great, if there's a huge amount of damage, P53 has an alternative pathway called apoptosis, which is programmed cell death. Operative word is death.
So if you get like a really bad sunburn when your
If
skin,
you have a really bad sunburn, you are going to lose some skin cells. They're going to die off.
so that's like the peeling. It's
Yes. Yeah. And so, as far as you're concerned, that's a far better alternative than allowing damaged cells to replicate. That's what this is all about. You've got billions of cells, and you have the ability in your stem cells to make new ones. It is way better to kill off a cell than to replicate a cell that has mutants in it that can then lead to cancer. After all, skin cancer from thymine dimers is at the second leading cause of cancer in Arizona, just behind smoking. And so this is a really critical process, and P53 is the protein that regulates whether the cell will commit suicide. It is committing suicide. Every cell in your body has a genetic subroutine, a genetic program. You have proteins sitting in your cell, ready to be activated at a moment's notice if P53 says it's time to call quits. And so that genetic program, or programmed cell death, is at a tipping point. All it takes is one little shove of P53, and that cell just commits suicide and gets replaced from stem cells. Yes?
So like, P53 can either kill the cell through apoptosis or cause the cell to halt. Why does that say for 60?
Cell cycle. Anybody else? Let's do another cell. So number 3 is a heterozygote P53 heterozygote, so you have lost P53 in one of your cells, wild type or cancer are the two alternative choices. Think about this for a minute. What is the phenotype of a cell that is heterozygous for P53? Is it normal or is it cancer? And then we'll vote again. Get you in the mood for voting. So by yourself, do this by yourself. If need be, then we can have a discussion. Everybody ready to vote? How many vote wild type for a P53 heterozygote? Raise your hands. How many vote cancer for a P53 heterozygote? So find someone who disagrees with you and have it without proof. Everybody ready to vote again? Yeah. How many vote wild type? Raise your hands high. How many vote cancer? Raise your hands high. Okay, wild type wins. Look, this nucleus is in a cell. So that's dead. But that gene is making P53 protein. It's just a normal, ordinary, recessive loss of function. Nothing fancy about it. You can get by with lots and lots of genes that are heterozygous for a dead partner. As long as you have one good P53, it shouldn't matter at all to that cell. And so this is what we talked about on Monday, the familial part of cancer. If you inherit a mutant gene from a heterozygous parent, then if you grow up and all the cells in your body are heterozygous, and as soon as you have one mutation in that gene anywhere, that gene is now homozygous recessive and has lost its gate, its checkpoint.
So because of less people, there's more inclined to necrosis?
No. So that really doesn't, there's a handful of genes that are actually, they're called dose-sensitive genes. Anyway, that's important. But the vast majority of your genes, you can get by. If you're heterozygous, well, there are lots and lots, hundreds of mutants we now know through sequencing. And so this is just an ordinary system. Unless you have inherited one mutant copy, that's the BRAC1 story, the typical story for familial BRAC1. Every cell in your body has BRAC1 mutant. You lose one BRAC, the second gene, and now you're a homozygous mutant.
Is there a difference in the amount of protein?
No, that's what he just asked. So the cell can adjust for that. It just transcribes it. Yeah. And so that, again, except for those sensitive mutations, those sensitive genes, you are heterozygous for hundreds and hundreds of mutants, and it doesn't seem to affect you. Anybody else? Okay. So fourth category, there's a very small category of a gene involving cancer is telomerase. You have a question?
Yes. So P53 negative can be inherited.
Yes.
What about
So retinoblastoma, remember. So there's familial retinoblastoma. That shows up really, really fast. P53 takes a little while longer.
well, what about like Raz negative?
Presumably, any gene can be mutant and inherited. Got it. You're heterozygous. But heterozygotes are okay.
But it's not hemizygous or heterozygous?
Oh, it's heterozygous. Hemizygous means you only have one copy of the gene. I only have one copy of all my X-linked genes. But I have two copies of RAS, RAF, P53RB. Hemizygous means one gene. Yeah. That's what we just did. Yeah, there's no problem with that. So number 4 is telomerase. Telomerase is ordinarily required for a cell that's growing rapidly, a cell that's growing. People thought that was going to be the magic bullet for cancer. Just knock out telomerase and we stop cancer. But telomerase is not the only way to lengthen the telomere. So while telomerase is always activated in a cancer cell, it is not the magic pathway. It is an alternative pathway. As I said, you can't get cancer from a single oncogene. You might get cancer if you knock out the DNA repair genes. These are recessive mutations where you have to knock out both copies. Oncogenes are dominant. Tumor suppressor genes are recessive. A typical cancer cell literally has hundreds and hundreds of mutations because it's lost DNA repair. But what you see is typically 2 or 3 oncogene mutations, 2 to 3 tumor suppressor mutations. And so in the cancer pathway, what you typically see in a cancer cell, and now because DNA sequencing is so inexpensive, hundreds and thousands of tumors have now been analyzed. There are thousands of mutations because of the loss of DNA repair. But typically in the cancer pathway, you only see a half a dozen to a dozen mutations that really matter. And that's the problem with analysis of tumors, because there's 1,000 mutations because of loss of DNA repair. You have to go through and ask for each mutation, does this matter? Does it give a small boost to cancer or not? And so that's taking a lot of time. Any last questions on signal transduction and how genes cause